Welcome to 3.3, page 3. Here we are to use the products of logarithms to expand the expression as a sum, difference, and or constant multiple of logarithms. So we're using those properties, those 1, 2, 3 properties that we've been taking a look at this section right here. So when I give this to you on a test or quiz, I'm going to say write this as the product sum or difference of multiple logarithms where the arguments are as simplified as possible. So because there's a product here, I can write this as log base 10 of 100 plus log base 10 of x. And that 100 simplified, however, log base 10 of 100, there's a chance we can work with that. And because I can write this as 10 to the second, it's a power of 10. We got it made. What is the exponent that turns 10 into 100? 2. I get 2 plus log base 10 of x. So now I have a much more simple, well, not much more, but a more simplified argument here. X is certainly more simplified than 100x. Log base 10 of 7 minus log base 10 of z. If you don't know where that's coming from, I recommend you go back and relook 3.2, but it is just our quotient becomes the difference of the logs. What is the exponent that turns 10 into 7? No idea. Well, some idea. It's less than 1, but that's about it. Simplify this one, I can pull the negative 3 out in front. Log base 6 of z. What's the exponent that turns 6 into z? Who knows? Now, radicals, third roots, square roots, etc., and logarithms, not quite as nice as logarithms that contain exponential fractional exponents. So this is ln of t to the 1/3, which by rule 3, property 3, we can pull the 1/3 out, ln t. What's the exponent that turns e into t? I don't know. All right, 56, we got a product, we've got a quotient, and ultimately we're going to do this in one step eventually. However, I'm going to do this one in 2 steps. In the big picture, this is a quotient, so I'm going to treat it as a quotient, ln xy minus ln z, and then take care of this product. ln x plus ln y minus ln z. But I don't think it's a stretch to see that that's pretty easy to do in one step. Okay, ln. This is the square root of x squared, which is x. Now, truthfully, it's positive value of x. Over the square root of y to the 3rd, that would be y to the 3 halves. It's y to the 3rd to the 1/2. And now I can split those into ln x minus ln y to the 3 halves. However, with property 3, I can pull that 3 halves in front and get a more simplified argument. And I don't think that's so difficult to see that we can get from here straight to there in one step. So try 58 one step. You probably might be able to do it in your head. I'm going to do that in one step. We've got exponents and we've got products. Every place there's a times becomes a plus. So this is log base 4 of x plus. My next term would be log base 4 of y to the 6th. So 6 log base 4 of y plus. My next term would be log base 4 of z to the 4th. So 4 log base 4 of z. Going to think of this in my head at the very least, if not rewrite it as x squared plus 1 to the 1/2. And that's a quotient. So that is ln of x minus, when I hit that division, it's minus. It's going to be ln of that whole denominator, but it has an exponent. So that's 1/2 times ln of x squared plus 1. Now, this is important. Terms. We do not have a rule over here that equates to that. I don't have. Yes, I have log plus a log, but this is log of a sum here. This is not sum of logs. So I've got this, but I don't have a rule for x squared plus 1. I can't make this ln x squared plus ln 1. I can't pull that 2 out because the whole thing's not squared. There is nothing I can do with that. If it was x squared minus 1, I could factor it and have x plus 1 times x minus 1 and then treat it as log of a product. But that one gets people. Right there. People are like, oh, I have to be able to simplify that. You can't always do that. Only if I could factor it could I simplify it. Okay, big challenge here. Notice that y to the 4th is not under the square root. A lot of times I'm like, hey, make sure you're showing your steps. I think we can do this in our head. Every place there's a times right here becomes a plus. Every place there's a division becomes subtraction. So I'm going to be at least thinking of this way. Log base b x to the 1/2 times y to the 4th on z to the 4th. So it's log base b of x to the 1/2 plus log base b of y to the 4th minus log base b of z to the 4th. But those exponents can pop out along the way. This is a one-step problem. Students are typically very, very good at this. So I get a log base b of x to the 1/2 log base b of x plus log base b of y to the 4th plus 4 log base b of y minus log base b of z to the 4th, which is 4 log base b of z. I'll tell you where people might miss this. If there was, let's say, an a right here, let's just say there was a times a. Okay, I made that one up, so you don't have to write this down. I just want you looking at this. Here's where people would miss this. They would then go, oh, and that's times, so plus log base b of a. Don't write that down. Do you see the problem there? It would truthfully be minus that whole denominator, and that negative would have to distribute to this. And that's where people make mistakes on the problems that start out looking like that. Okay, so pretty quick page there, I believe, but not to say there aren't going to be some questions along the way. The only reason they have this x is greater than 1 is because if x is a little bit less than 1, this top becomes 0. It doesn't really have to come into play for your problem at this time. So it's just a little twist. That is probably about a 5-minute page for you, maybe maximum. Please let me know how I can help.